Okay, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1203. I think we should just get into it. Let's see here, because we were sort of in the middle of something last time, so I guess we're going to just finish up. Hold on. Make sure I can see the chat here. Okay. So we did some continuity examples last time, which is kind of a spillover from the time before that. But the main thing we spoke about was attacking the rate problem. So we actually solved that. We solved the rate problem, at least in some special context. And we'll talk about that, I guess, a little more today, next time. Basically, we figured out that in some sense, we could think of slope as synonymous with speed or velocity. And so using that idea, we figured out a way to find the slope of a curve by equating that to the slope of the tangent line to that curve, which is the white line here. And we also came up with an argument that showed that that expression, that limit, will give you the slope of the tangent line, which, as many of you know and have seen before, is the difference quotient. So that's why that expression was so important, except prior to this, you never really saw it with a limit in front of it, probably not if you weren't in calculus. And so now we put a limit in front of the difference quotient as the denominator is approaching 0, and we get something that we call the derivative, right? So this was the solution to the rate problem. It solved the rate problem in some special circumstances, but those circumstances are actually pretty broad and applicable. So we spoke about some notation, but then we used the definition in a different sized font to compute the derivative of some functions, as well as answer a question about tangent lines, which that's an important kind of question to know. Like, that's guaranteed something that's going to come up. Very traditional Calc 1 question. And then we went through some other examples where we have used the definition of the derivative to find a couple other derivatives. So what we want to do now is just finish up 2 more examples, and yeah, then we'll continue on. So I also introduced that shortcut notation to you, so that's good. So let's actually just move on. Okay. Oh. Right there. I don't know what was going on, but yeah, so let's continue with our examples. So this one, we want to find the slope of this function, or the derivative of this function. And you might notice that this one is not as obvious as the other 2. So we knew by interpreting the derivative as slope, what the answer to the last 2 was supposed to be kind of obvious, because I asked, what is the derivative of a constant? Now we know that a constant function is just a horizontal flat straight line. The slope is 0, we know that. So by going through the limit definition of the derivative, we should get 0 as the answer, and we did. We also did an example of what is the derivative of a constant times x? And we know that if y equals a constant times x, that's just a straight line going through the origin. And the line is vertical, of course, is not going to be defined, but you can't write it as y equals c times x anyway. So if it's non-vertical, then if it's horizontal, you'll get 0, which we actually computed before. If your c is positive, it will be a line of positive slope. C is negative, be a line of negative slope. But in either case, c should be the answer, and that was the answer we got. Here, though, things are kind of different. This guy, looks like this, which means that his slope is not really obvious, actually. We know that something we can say is that the slope should always be negative, I guess, because if you have a tangent line at any of these points, the tangent line is always pointing down, as you might notice. So we can say it's always negative, but as for what its value is, how do you know? This one is changing. It's curved. So let's actually see what the derivative of this guy is. So here, we know that f prime of x equals the limit as h approaches 0 of f of x plus h minus f of x all over h. Okay, so that's the definition. Write it down every time so we don't forget. Of course, plugging that in here, we have 1 over x plus h minus 1 over x all over h. Nothing strange here. We've seen this a lot, even on day 1 of this class. So we know that this is a compound fraction. The easiest way to simplify those are to multiply and divide by the LCD. So that's what we're going to do. Of course, it's going to be distributed in the top, and that's going to multiply into the bottom. So in the first case, the x plus h is canceled. We're left with x. In the second case, the x cancels. We're left with x plus h. In the denominator, we have this. Remember, do not expand the denominator. You almost never want to do that. You can be in a situation where you want to expand temporarily, but that would be for the purpose of refactoring it. Here, it's already in a factored form. You do not want to expand it. And here, what we did was multiply and divide by LCD. Which is the standard trick here. Now we would have x kills the x. We would end up with minus h over hx x plus h. This is going to, now the h's die. And now you'll notice that I can plug in h equals 0 without immediately getting division by 0. And so minus 1 over x squared. Okay. Now, of course, x not equal to 0, but that was true from the beginning. So it's not like the derivative messed anything up here. Beginning. We start with 1 over x. X couldn't be 0 in the first place. So it's not going to be 0 now. That's actually something that we'll talk about in a little bit. So that is the derivative. One thing I want you to notice is that, note, this is always negative. Right? Which makes sense by our intuition. If you look at the tangent lines to this curve, yeah, they'd all be negative. They'll all be pointing down slightly everywhere. So here, because you have an x squared, the x squared is always 0 or bigger. It's not 0 in this case, so it's always bigger than 0. So this part is always positive, and then you take a negative of that. So now you get something that's always negative. Interesting. To remind you of a notation, how we can say this in as a shortcut, this means I can say the derivative of 1 over x is 1 over x squared, right? So this guy, now you can take as a rule. I would say you don't have to memorize, but this guy shows up pretty often. You'll probably end up memorizing it anyway, but I'm going to actually show you guys something eventually that's going to cover this if you memorize that. So you probably don't even have to memorize right now. But yeah, that's that. Here's another one. Again, the answer here isn't really obvious. Square root of x looks like starts at 0 and then goes off here. So if you were to try to find tangent lines, in this one here, the tangent lines are always positive, and they always seem to be above the curve. We'll actually talk about that in a little bit also. But yeah, they always tend to be positive, it looks like. They tend to be 0 or bigger, but we will see. But other than that, there's nothing really obvious that I can say here. Let's just jump into what the derivative tells us by definition. Again, writing down the definition. This will be x plus h, times that, all of that. Standard trick here, because those are square roots, is to multiply and divide by the conjugate, which is just change the middle sign because it's only a square root. And you want to take advantage of the difference of squares formula. So this is going to multiply across there, and these guys are going to multiply out. I won't even think of them as distributing because it's in the form of the difference of squares formula. It's like an a minus b times an a plus b. So I kind of know what that's going to end up like. It's going to be the a squared, which is this, minus the b squared, which is that. Again, do not just expand the denominator. These x's will die. Now if I plug in h equals 0, I'll get 1 over radical x plus radical x, or 1 over 2 radical x. And yeah, that's actually the derivative. So I can say here the derivative of the square root of x is 1 over 2 rad x. You can also think of this as a rule. But again, I would say you don't really have to memorize it here either. We'll talk about that later. So far, everything I said could be memorized, but you don't have to technically. And I'll talk about that 2 classes from now or something like that. Okay, so that is actually a very basic rule because the square root of x is a very common function. It's going to show up all the time. If you know how to differentiate it just by looking at it, you know what the answer is. That would be nice, but you don't need to directly memorize it, I don't think. Okay, so those are the examples just for you to see how we can use this formula. And of course, you'll notice that that guy is always positive. And of course, here x is not 0, which is kind of weird because x could be 0 in the first place, but you'll notice that at 0, there's no left side, so you can't actually take the limit from the left. And so that's an issue. So it turns out that there are issues at 0. There's really only a limit from the right. And so this is, this guy has domain, of course, x strictly greater than 0. So that's at 0, there's an issue, as well as x less than 0. Okay, so I think that's it. Nothing really to say there. Let me see, there are some things that I want to see. Did I tell you that before? No, okay, so let me tell you that. So the rest of this class, and probably a decent chunk of next class as well, is going to be somewhat like an information dump. So we're going to be talking about a lot of facts surrounding the derivative and how you should interpret it, how you should think about it, because that's going to be important later for when we're doing applications and all sorts of things. So that's what we're going to kind of get into now, talk a little bit more about derivatives like in general. So it'll be a while before we do any straightforward computational examples like this, but I need to set it up so that when we're going to do that again, you kind of know what you have to do, when you have to do it, why you would use a derivative in certain situations, etc. So let's talk more about that. Do you want to mention, let's make sure that I spoke about, no, I don't know which of the basic facts I told you about before. Yes, I did talk about the notation, the Newton's prime notation and the Leibniz notation. Okay, cool. So I don't need to introduce any notation here. So let's talk about interpretations. Very important. So f of x is a differentiable function, meaning a function that we can find the derivative of. Not all functions are like this, by the way, and that's one of the caveats of this solution to the rate problem. It's not always true that you can find the derivative of a function. Functions where you can, they're called differentiable. F prime of x is its derivative. What are some interpretations of that derivative? So yeah, I mean, it is the derivative of f at x. What does that even mean? Well, it means the slope of f, actually. So slope, derivative, these guys are actually synonyms, right? Synonyms. Pretty sure I spelled synonym wrong. Okay. I think my bad handwriting can actually cover up the fact that I don't remember how to spell that at the moment. Okay, so they're the slope, right? So derivative is the slope. Derivative is exactly the slope. It's just used in a different context. So we say the word slope when we're talking about straight lines. If you want to talk about whatever idea slope conveys in general, we would use the word derivative. So we can use derivative to talk about slope in general, in a general context. It doesn't have to be a straight line context. So the derivative, you can think of it as the slope of the function. More specifically, it's the slope of the tangent line to the function. So you can think of it as the slope of the function, the slope of the tangent line to the function at a certain point of interest. You can think of it as, it's called the instantaneous rate of change. So that might be a phrase that you'll see in your homework. Instantaneous rate of change. Okay, so we saw that there was a concept called the average rate of change, and we actually used the concept of average rate of change to figure out what was going on, not over a whole interval or time period, but in an instant, a very small time period. So this is called the instantaneous rate of change. And that's a phrase that you might see in your homework. It might actually find the instantaneous rate of change. It's just another way to say derivative. In terms of more into what it can tell us, you can talk about it as being how fast y equals f of x is changing in relation to x. So every time x changes by 1 unit, how many units will your y change by? And what is that answer at every instant, right? So to answer a question like that, that would be called the derivative. It's kind of telling you how fast the output variable is changing in relation to the input variable. I guess you can say, finally, you can say the derivative gives a formula for all the above. So you can think of the derivative as being all the above, but you can also think of it as, this is the thing I do to get a formula to tell me about the above. It's the same thing, right? So yes, the derivative is the slope, but it's more than just a slope. You can literally think of it as a formula. This is the formula I can use to find the slope at any point. So these interpretations are important. So whenever you want to find something that's similar to one of these, that's how you know you'd use the derivative. So if a question says, hey, blah, 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 tangent line, blah, 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 you automatically know that derivative is going to be involved in there because the derivative is the slope of the tangent line, right? Or there's a blah, 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 how fast is blah, blah, blah at this instant? You know that you're going to need the derivative because this is one of the interpretations, okay? Let's talk about higher derivative. No, not yet. I want to talk about the interpretations of the sign of the derivative. So I made some comments up here about, oh, look, this derivative is always positive, and then this derivative is always negative, and so on and so forth. And I just actually want to say that me saying those words actually goes beyond just me noticing some peculiarity of this particular graph. It is something that you can talk about in general. So notice here, to kind of give you the idea, I'll draw several. 1, 2, 3, 4. So consider these. I'm going to draw some straight line examples. So the first line looks like this. The second line looks like this, say, it's horizontal. The third line looks like this. And the fourth line looks vertical. Okay. Now, I want you to tell me about the slope in each of these cases. So tell me about the slope here, M. What can you say about this slope of the line that is pictured here in terms of the sign? Is it positive? Is it negative? Is it something else?
Is it positive?
It's positive, right? It's positive. It's moving up as you go from left to right. It's positive. So this means here slope is positive, which of course means the derivative is positive in particular. Right? So that's what I kind of want to point out. What about the second one?
It's equal to 0.
It's equal to 0. Here the slope is 0. It's a horizontal line. And here?
Negative.
Slope is negative. So the derivative is negative. Of course, going to make some generalizations on this. What about here, the last one? So this one has no slope, or slope undefined. which means the derivative is undefined. Yeah. Derivative is undefined. So, as I mentioned, you can't always find derivatives, and we're going to talk about that at length at some point. But yeah, so it turns out that we can actually make, based on the above, we can actually talk about the sign of a derivative and what it actually means. It turns out that you can talk about the sign of a derivative as indicative of all these behaviors, meaning something is going up as you go from left to right, or something is just flat in the region where you're looking, or something is going down as you're going from left to right, or something is like vertical, or maybe some other things. We'll talk about where the derivative is undefined in other cases as well, but it's undefined in this case here. So this leads to the following. Let I be some interval around x. Then we can say the following. F is increasing on I if f prime is greater than 0 there. Okay, so it turns out you can think of the derivative being positive as synonymous with increasing. Increasing means basically going up as you move. Someone's trying to get in here. I don't know. Going up as you move from left to right. Right? We call that behavior increasing. We say f is increasing here, versus f is decreasing on I if our derivative is negative there. And these two things are some important facts that we can get about the behavior of a function based on the sign of a derivative. So the sign of the derivative actually matters. It tells you when you're increasing or decreasing. So you'll notice here, in the case of the square root, this function, the square root function, is always increasing. I want you to pay attention to the fact that the derivative is always going to be a positive number, right? It's not coincidence. It's like it has to be that way. This guy, no matter what branch you're looking at, it's moving down as you go from left to right. It's always decreasing. It's not a coincidence that the derivative is always negative, right? So that's something I want you to be aware of. The sign of the derivative actually matters. Okay, and you can actually make some interpretations because of it. So it turns out just by figuring out how fast something is moving, we can also figure out, is the thing increasing or decreasing at the same time, which is very interesting. We'll talk about that in a little bit. What I will also want to talk about at this point is the notion of higher derivatives. So it turns out sometimes we can take derivatives repeatedly. It's pretty much always going to happen in this class. But there are some functions where you can maybe take a derivative once or twice or several times, but eventually you get to a point where you can't take derivatives anymore. The result is going to be something that you can't take the derivative of. You're never going to see such a function in Calc 1, but sometimes you can just keep taking derivatives forever, infinitely often. i.e., so you're like, you can take the derivative of the derivative of the derivative dot dot dot. Okay. These derivatives are called higher derivatives, right? So derivative of derivative. This is called the second derivative. And then, of course, you can get the third, you can get the fourth. Sometimes, and these guys are called the higher derivatives. Right, so it's derivatives beyond the first derivative, which now we're going to qualify the derivative that we've spoken about as the first derivative, because a lot of times it's possible to take more derivatives. And so it leads to the notion of higher derivatives. These higher derivatives can be useful in various applications. And I'll talk about that in a little bit, but first let's introduce the notation of the higher derivatives. So we have Newton's prime notation. I don't think that was much better. Leibniz notation. And the derivative that they represent. So our original function, f of x, actually, say in Leibniz we would call it y. This is called the zeroth derivative. So this is the function actually after we've taken zero derivatives. We already know the notation for the first derivative. So this is the first derivative. Or if someone just says derivative, they're talking about the first one. What would the second derivative look like? Well, in Newton's notation, you just add another prime. So you have f double prime, right? That's what we would call it here. Do I want to write that down? F double prime. That's how you say it. You don't say f prime prime. You say f double prime or f triple prime, etc. The Leibniz notation would be d squared y dx squared. So if you see that, that's talking about the second derivative. Why does the Leibniz notation look like that? Well, this is like you had the derivative, and then you take the derivative of the derivative. And so you have the d squared, the y is there. The y is always thought of as something that you can just shift off separately. It's a separate function. And so you have a d squared, and at the bottom, you have the dx squared, the change in x squared. And so that's how you'd write the second derivative. You can write the third derivative as well. Just f triple prime. And here you would be that. So you can keep going like this. Eventually, though, you'll realize that if you take a lot of derivatives, eventually writing all these notches in the Newton notation is going to be very annoying. So there comes a point where for like 4 derivatives or higher, usually it starts around 4, we kind of switch up the prime notation a little bit. We write the number of derivatives as a power, but we put that power in parentheses. So it's going to look like this, f parentheses n of x, right? So in this case, I'm going to give you a very specific example. Let's say 17. So if I put f to the parentheses 17, it doesn't mean f raised to the 17th power. It means I'm taking 17 derivatives. This guy here is going to be d17 y over dx17, and this is the 17th derivative. In fact, sometimes even the 0th derivative is denoted like this, with a 0 in parentheses of x. Right? Depends on the context, though. We're pretty much never going to be in the context to actually say that. But yeah, that's the general notation here for higher derivatives. So we write f to the n in parentheses of x, or dny dx to the n, to represent the nth derivative. And of course, it's provided these derivatives exist. We'll talk about the existence of the derivative soon, but we already kind of know that the derivative can't always work, because like, what would a vertical line's derivative be? Well, a vertical line has no slope. It can't have a derivative. Derivative is undefined, right? So the derivative is a limit. So kind of we know how limits work. It's possible for a limit does not exist. So it is possible for the derivative not to be defined somewhere, or not to exist. So just throwing that out there. We'll talk about it eventually. But yeah, sometimes we can take higher derivatives. We can take it repeatedly. This will be the notation for it. So if you see that. And now I actually want to focus for us. The focus is going to be on the second derivative. For us, the second derivative is going to be the most important higher derivative. Right? So there's going to be no real reason in terms of application or problems that I want you to solve where you're going to need something higher than the second derivative. If I ever ask you for a third derivative, and I wouldn't ask you for higher than that, but if I ever did, it would just be a computational thing for me to test. Do you understand when I say third derivative, what you're supposed to be doing? You're supposed to take the derivative, then take it again, then take it again. You're supposed to take the derivative 3 times. But I'll just test you like that on like a computational level. I'm never going to ask you to do anything with the third derivative. The second derivative is going to be important, though, because the second derivative, we're going to have some very important applications. So I want to take some time to talk about the second derivative for a second. Pun wasn't intended. Let's talk about the second derivative. This is the derivative of the derivative. Two important applications for us. One, the physics of motion. So let's say t is time, and we have a function that we call s for traditional reasons. And let's say this is the position function. Okay, so that's like your current location at time t. It turns out we can take the first derivative as prime. This gives us a function that we call v of t, or the velocity function. And velocity is speed in a particular direction. In Calc 1, there are only going to be two directions to worry about in general. Either we're looking at a scenario in which the directions are left and right, or we're looking at a scenario in which the directions are up and down. Traditionally speaking, moving to the right or moving up is considered the positive direction, while moving to the left or moving down is considered the negative direction. But this is called the velocity function. So this guy is the rate of change of position. Okay, and this one is just position, which is talking about your location at time t. And so if someone asks the question, where are you? Where are you at, yo? You would look at the position function. If someone else asks instead, how fast are you moving? Then the first derivative is something that you can answer that question with. However, in this context, there is something called the second derivative that can often work. We call this function a of t, right? And it's actually the first derivative of velocity. But you can think of it as the second derivative of position. This guy is called the acceleration function. And it's how you can interpret this is that it's the rate of change of velocity. What does it mean to be the rate of change of velocity? Well, the kind of question that this function would answer is the following. Are you speeding up? Or slowing down? Right? Notice that these are three very different kinds of questions. Where are you? How fast are you going? And are you speeding up or slowing down? Right? So the different derivatives can answer different questions. They have different interpretations, different meanings. The second derivative of position, the interpretation would be whether or not someone is speeding up or slowing down. So usually, of course, if the acceleration is positive, it means you're speeding up. If the acceleration is negative, it means you're slowing down. Also, for those of you who have taken physics before, especially if it's not calculus-based, what you'll notice is what you probably didn't notice is a lot of the forms that they were giving you that they're just like, here's the formula for this thing. Oh yeah, by the way, here's the formula for this thing. What actually happened was that they used calculus in the background to derive those formulas. But because you were not in a calculus-based class, they never showed you that. They just gave you the formulas at the end of the day. But it turns out that knowing the position, or more specifically, especially in like basic Newtonian motion, they start with the acceleration and then they reverse the derivative to figure out the formulas of the other ones. So calculus is going on in the background there. But this is one important interpretation or application of the derivative, and specifically the second derivative. It can tell us about acceleration, right? So how fast you're moving. The third derivative has a nice physics application as well. It's called the jerk, right? Like that's literally what it's called. So, you know, if you have a friend who calls you a third derivative, they're not saying something nice, just so you know. I've seen this on t-shirts before, and everyone's laughing at it and not knowing that the t-shirt is calling them a jerk. Okay, so the second thing is this thing called concavity. which might seem like a very strange word at first, and I suppose it is, but I'm going to tell you what this word actually means right now. There are two kinds. It's for us. There is what we call concave up and concave down. Let's take them one at a time. Concave up.
What if it pays monthly? They don't do that.
Okay, so concave up, this means, let's say, f of x is concave up on an interval I if it always lies above its tangent lines on I. So a concave up function is a function where if at any point you were to look at its tangent line, the function itself is going to be on top of the tangent line, right? So that's a concave up function. Not all functions will have that property. When sketching the tangent line would kind of cradle the function. It'll be on the bottom, right? The function itself will be up on top of the tangent line. So that's called concave up. Now, what I want you to notice is the slopes over time are, what do you notice about the slopes here as you move forward in time from left to right? What would you say is happening to the slopes?
They're increasing.
They're increasing. Notice that the first one, the tangent line is pretty flat, which means its slope is close to zero. But as I go on, the tangent line keeps getting steeper and steeper. So the tangent lines are becoming more and more positive numbers, right? The slopes over time are increasing. But how to interpret increasing? Well, we just saw a little while ago that a function is increasing if its derivative is positive. So the slopes are increasing, but what is a slope? A slope is a derivative. So this basically means the derivatives are increasing, or the derivative function is increasing. What does it mean to say that the derivative is increasing? Well, that means that if I looked at the derivative of a function, I know that a function is increasing if its derivative is positive. But if I look at the derivative as the function itself, this is saying that the derivative of the derivative is positive, right? In other words, the second derivative is positive whenever a function is concave up, i.e. f is concave up on I if and only if the second derivative is positive on I. Then it will exhibit this behavior. If you know that the second derivative is positive, then it means that the function is being cradled by its tangent lines. Now I'm going to tell you another mnemonic, another way to think about this pretty soon, but let's just actually look at a concave down. Similarly, f is concave down on I if it lies below its tangent lines on I. So what would that look like? So you can have a function here doing its thing, but notice that whenever you draw a tangent line, the tangent line is above the function. Right? The tangent line doesn't slice through the function, or it's not underneath the function. It's always sitting on top of the function. This is called concave down behavior. I want you to notice here, slopes are decreasing in this case. And so that means the derivative is decreasing. And that, of course, means that if I were to take the derivative of the derivative, which gives me the second derivative, that would be less than 0 by what we learned before. So this leads to another important fact. F is concave down on I if and only if F double prime is negative there. So if you want to know when a function exhibits this kind of behavior, it's always below its tangent lines. What you can do is you can check the second derivative. So this talks about the second derivative. One of its applications is to identify different types of concavity, as we call them. Now, I want to make an important note. Important note. Concavity is about shape. Right? So it's a very common error for students to think that the second derivative being positive tells you something like the function is increasing, or it tells you something like if the function itself is positive or negative or not. It tells you none of these things. Concavity is purely a matter of shape. You will notice that for a function to behave in either of these ways, it would have to actually shape a certain way. You don't have to be increasing or decreasing in order to shape a certain way, but the concavity is about shape. So I want to make sure you get that. So when I say concave up, versus concave down, what I want you to think of is shape. So this has nothing to do with increasing, decreasing, etc. Or positive or negative, positive or negative values of our original function. It has nothing to do with that. It's purely about shape. You can be concave up while increasing, right? That's that. You can also be concave up while decreasing. In both of these situations, if I were to draw tangent lines, they will be below the function. So I can be moving up as I go from left to right or down as I go from left to right. It doesn't matter. Concavity is going to talk about shape. It's concave up if it's shaped in such a way that the tangent lines will always be below. Versus concave down, I can be concave down and increasing, or I can be concave down and decreasing. So here, this is concave up and increasing. Here, this is concave up and decreasing, right? So your concavity has nothing to do with increasing or decreasing. You can have either concavity and be doing either increasing or decreasing motions. It does not matter. Here, this is concave down and increasing. and this is concave down and decreasing. So you can have either or. Now, there is a mnemonic here. We say concave up like a cup. So concave up means you're shaped like this. You're like a cup that can hold water, or like a smiley face. You're happy, you're smiling. Concave up like a cup. You're positive, you're feeling positive. Your second derivative is positive. Everyone's positive. Concave up. Or you can say concave down like a frown. So you're feeling down, you're sad, you're frowning. Second derivative is negative, you feel negative. All right. So whenever you're talking about concavity, you know that you're talking about the second derivative. So the second derivative being up or down either means you're positive or negative. When you feel positive, you're happy, you're smiling. When you feel negative, you're frowning, you're down. Okay, so it's about the shape. Are you a smile or are you a frown while you're doing whatever it is you're doing? That's the important thing. And so what else I want to tell you about? So that's very important. Points of inflection. An inflection point of f is a point on the graph of f at which it changes concavity. So there are certain behaviors that our function can do. Let's say while it's increasing, so I can have my function do this. So it's going up the whole time, or I can have my function do this. Or if it's decreasing, I can have my function do this. Or I can have my function do this. Right? And you'll notice that something changes around this point right here. So these blue points are called points of inflection. Why is it called a point of inflection? Well, before that point, from there back, you are concave down. After that point, you are now concave up. Once you pass through that blue point, you have switched your concavity, right? You were concave down first, then concave up. In the second example, it was concave up, then it switched to concave down. In the third example, it was concave down, switched to concave up. In the last example, it was concave up, switched to concave down, right? And when you pass through a point where this change happens, such a point is called an inflection point. Now, inflection points are themselves very important. And what I want you to know is that we can identify when they occur by looking at the second derivative. Notice that the second derivative on this side would be negative, while the second derivative on this side would be positive. So we can identify when inflection points occur by identifying when a change in the second derivative, the sign of the second derivative occurs, right? Now, why is the above important? Well, consider what these pictures mean when some interpretation is given to our variables. So let's talk about some stuff, which I'm just gonna like verbally say here. Let's say the application I care about, right? Because students, they tend to not care about math, but math is just this thing that they learn and they never worry about it ever again after they pass the class. But yes, math is teaching about functions and these weird things, and you're like, okay, that's cool, dude, but what does it all mean, Basil, right? So I'm going to tell you what it means. Why is it important that we're able to find these things? Is because the interpretation, when we're looking at a picture or a graph of something, the interpretation that can follow based on what that picture is about. So let's say, for example, I am a business owner and the function that I'm caring about, the function that I'm looking at is tracking my profit, right? So the profit I'm making week over week, right? So I'm looking at my profit for our current first 1 week to the next, and I can see one of these 4 graphs on that picture. Now, the question is, which of these pictures would be the best picture for me? Which one would I really want to happen? Can anyone tell? What is the best case scenario if my interpretation of X was weeks and my interpretation of Y was profit? Which one would you want to have? Like, with that interpretation, is one better than the other? Or are they all the same? Like, no matter which graph here, you'd be fine with it? It'd be cool?
I'm gonna go with the first one.
The first one. Yeah, that would be the best case scenario if I took the interpretation as profit. Now, let's take a slightly more morbid example. The graph is now the size of a malignant tumor that, let's say, someone was diagnosed with. What would be the best graph in that scenario?
Wouldn't it be the last one?
It would be exactly the last one, right? What is good or bad is going to change based on interpretations. It's not just a picture. It's not just a function. It has meaning when you give it meaning. And then you're going, when you really start to think about that, you probably intuitively know why one was better than the other in one of those situations. But let me explain to you exactly why. What does it mean to be concave down and increasing? I think did I erase something? No. What does it mean to be concave down and increasing? What it means is that you're increasing, but you're increasing slower over time. So you're increasing, but you know, your increase is slowing down. You're still getting bigger, but the increments by which you're getting bigger is getting smaller over time. Versus, I don't know why I jumped there. Versus, if you're increasing and concave up, it means you're increasing, but you're getting bigger over time. The increments by which you're increasing is increasing itself, right? So you're increasing by more and more every time. And so this can matter. And so a lot of times when people just look at something from, let's say, a first derivative level of thinking, all they can tell is, oh, something is moving up or down, whatever it's doing. But when you move on to the next level, the second derivative level of thinking, it now gives you more emphasis. It's not just that we're moving up slower, we're moving up faster. So for example, to pick a more controversial example, because I'm always about that, you can look at something like global warming. And people will tell you, oh, you know, the planet has always been heating up. That's been going on for millennia. Yeah, but how it's going up is different. It's going up faster and faster now than it ever has before. It's like, yeah, pre-industrial revolution, that's how the graph of the planet looks like. Post-industrial revolution, that's how it looks. Yes, overall, the trend is upward, but it's a different kind of upward. And you need to go to a different level of thinking to kind of realize that that's what's going on, right? It's not just about going up or down, but how you go up or down matters. Whether you're going up faster or you're going up slower can matter. So in the first example, I would want the leftmost graph to be my profit, because what that means is I'm profitable, I'm making money. I may be making less over time, but hey, something happened at this blue dot. Maybe we introduced a new product. Maybe we got a different kind of marketing. Maybe we expanded into a new market or something. But after that blue dot, phew, now our profits took off. Whatever happened at that blue dot, I would want to know, because we probably should be doing more of that thing. How would I identify what that thing is? Well, I need to identify the inflection point. Knowing how to find an inflection point will tell you how to find that thing. Versus the second graph, it's like, yeah, we're profitable. We were awesome though. We were getting better and better every week, but something happened and suddenly, yeah, we're still making money, but I think our customers are losing interest. We probably should pay attention to like what happened. Did a competitor drop a new product? Did a competitor change their marketing strategy, right? So here, the second graph is like, yeah, we're good, but we probably shouldn't be too optimistic about the future. Something bad could be on the horizon. Versus in the last scenario, they're both bad for profits. You're losing money either way. But you know what? The third graph, there's a little hope. We are bleeding money, but we're bleeding it slower. So, I mean, something we're doing is making things a little better, right? Versus the last graph where it's like, man, we're losing money and now we're losing it faster than ever. Something is going on. Whatever we did to try to fix the problem made it worse, right? And knowing how to read that on a graph is important. Similarly, by a similar vein, if someone was diagnosed with a malignant tumor and you're tracking the size, they would want to know that the tumor is not only decreasing, but it's decreasing faster and faster. So whatever our doctor is doing, whatever my treatment is, it's working better and better over time, as opposed to in the third graph, yeah, it's still working, but the effectiveness seems to be slowing. Maybe I'm gaining a resistance to the treatment. Maybe something is going on. Yeah, we're still, overall, it's good news, but it could potentially not be so good in the future, right? Whereas either situation in the first two is bad, but the situation on the most left is worse, because it's like, yeah, the tumor is growing, but now it's growing faster than it was before. Like whatever is going on, it's not good. Something has changed for the worst. And being able to identify that is identifying concavity. It is identifying inflection, right? So the second derivative is important because it allows us to talk about things like, of course, velocity and acceleration, but also it allows us to talk about properties of functions in terms of concavity, in the sense that it can tell you if something is increasing, is it doing so slower or faster? Is the rate of increase speeding up or slowing down? Versus if something is decreasing, is it doing so slower or faster? And this might be important for you to know. And so there are going to be two important tests for us to know, and I'll just tell you the names and we'll get to them next time. To identify the properties above. So let's say, for whatever reason, I've convinced you that knowing about these things is important. How do you actually go about finding them out? Right? So one is called the first derivative test. Obviously, it involves the first derivative. This is used to find where f is increasing or decreasing. And bonus, it turns out we can also use it to find where f has maximums or minimums. It turns out by solving the rate problem, just answering the question of how fast something's moving, we're getting all sorts of other answers for free. We can now tell if it's increasing or decreasing, is it moving up or down? And we can also tell where was the peak, where was the valley. We'll see how the first derivative test tells you that next time. Second test is the concavity test. So this is the test that would tell you about, well, concavity and inflections, used to find the concavity and inflection behavior effects. Is it concave down? Is it concave up? Did an inflection occur? Did the concavity change? If those are all your questions, you want to do something that's called the concavity test. Obviously, since we know that concavity is determined by the sign of the second derivative, the concavity test involves using the second derivative. Now, there's a third test that we're going to ignore, essentially. Third test. There's a test called the second derivative test. Jhevon will ignore. Not because it's not cool or important, because every calculus textbook that talks about this is going to tell you about it. But the thing is, the information you get, it also tells about increasing versus decreasing. And it tells you about, that's the only thing it tells you about. So it's like, if you went through the first derivative test, you would find out the same information that the second derivative test would give you, and you'd actually find out more information, right? The second derivative test gives you the same information as the first derivative test, but it actually gives you less information. So it's like, if we're going to do the first derivative test and the concavity test, the second derivative test is superfluous. It doesn't really make sense. It's not worth doing. You already have all the information you would need. And pretty much in this class, for the things I'm going to be asking you to do, you're going to have to do the first derivative test anyway. So once you kind of do that, the second derivative test would be useless. So I'm essentially going to completely ignore it. You're not going to need to know about it. The first two tests, though, are the ones that are important. But this one you can actually forget about. I said it here because it deserves an honorable mention, but it's basically using the second derivative to get the kind of same information that you would from a first derivative in a backdoor way, but it gives you less information than you could get from the first derivative test, so it's not really worth it. So next time what I'm going to do is I'm going to describe, because I think our time's up, I'm going to describe these tests in detail, how you can use them, talk about some other properties of the derivatives and the existence, and I don't know, maybe we'll get to some calculation type stuff. But a lot of next class is also going to be some information / concept dump because it's going to be important in the future for the applications we're going to want to use. So we will end there. Hopefully you understood everything that was clear. And yeah, I'll end there. I have office hours with a couple students in a little bit, so I have to go right now. Hopefully you guys have a good rest of your day and a good weekend, and I will see you guys in the next one. Ciao.